In section 20, we're going to be looking at properties of logarithms. We'll be taking a much closer look at how logarithms combine together, and we'll see how they're connected to their exponential counterparts. So for example, if I was to give you the statement, let's say x squared times x to the fifth, then we could combine those together using 1x and by adding the exponents. And so we would get the result x raised to the seventh. This is a property of exponential statements. There's another property like this with division. So if I was to take x squared and divide it by x to the fifth, then I can combine those together using 1x by taking the numerator exponent and subtracting the denominator exponent. The order of that subtraction is very important. It's always numerator minus denominator. And then we would eventually say x raised to the negative third power. So the logarithm has properties that are similar to these kinds of exponential properties. So I want to get you thinking the correlation between exponential and logarithm here. So for Theorem 20.1, I want to introduce the three properties that we're going to start the section with, and these are known as the Laws of Logarithms. And I'm going to go straight to statement number 1, and then I'll go back and talk about the first line in the theorem. The first statement says, if we have a log base b with m multiplied with n inside the argument, then that is going to be equivalent to having log base b of m plus log base b of n. This is known as the product rule for logarithms. It is very similar to this first statement we made about exponentials down at the bottom. I have a product in exponentials between the two exponential statements, and then I can combine the two into just one by then using addition with the exponents. So there's still this connection between multiplication and addition, and then 2 becoming just 1. And that's exactly what's happening here, but it's in the inverse order. Since logarithms are the inverse of the exponential, we do expect there to be a great deal of similarity, but there's also their differences. So this again is called the product rule. Now there's a lot of letters going around here because I'm giving you the general theorem, and we're going to see some examples of some specifics. So what you need to know is that the m and the n always have to be greater than 0 because they represent arguments. The domain of a logarithm always has to have the argument being greater than 0. So both m and n have to be values that are greater than 0. B, which is being used for the base, this is the same base that we've been using since exponentials. It has to be positive and it can't be 1. And then the rest of this beginning line just says that everything has to be a real number. So just everything's a real number, and we'll be fine with those. Statement 2 is called the quotient rule for logarithms. We have division in the argument of this single log, just one single log with division in the argument. That is equivalent to having 2 logs with the same base, but then we have subtraction in between those 2 logs. And it's important to notice that the numerator ends up being the first argument and the denominator ends up being the second argument, much like we had to think about the order of the subtraction on the second example with exponents when we had x squared divided by x to the fifth. That division would take the 2 exponential statements and turn it into 1, but then we had to do subtraction of the numerator minus the denominator. So that is definitely some consistency there with the quotient rule for exponents and for logs here. And then the last rule that we're going to look at here for logarithms is called the power rule, or the power property, power law. This says that if there is a power attached to the argument, then we are permitted to bring that down in front and have it multiply with the logarithm. In other words, p is multiplied with log base b of m. So we're going to see in the upcoming examples where these properties can be used for what we call expanding and condensing of a logarithmic statement.